All right. So we'll start with how we to solve with this. So hope all of you have watched week 12 lectures. Okay. All right. So this is a very straightforward question. I think week 12 there is not much that is being discussed. So we'll go through some of the questions that we have for week 12. So the very first question that is there is so you are given the loss function for a few algorithms, and you have to identify like which losses are these that you can see in the figure. So what about option A? What loss is that? These are directly from the
Regression.
lectures.
Regression.
Regression, yeah. So this is basically our squared loss. This is our, yeah. So this is my squared loss. What about option B? Where
Logistic
did you say?
regression.
Yeah, this is logistic loss. This is the loss that we saw when we were doing logistic regression. What about option C?
Support vector machine.
Hinge
Yeah, so
loss
this is called hinge loss.
is
And the
perceptron.
fourth one is perceptron, which is modified hinge loss, right? Yeah. So these are the loss function that we have seen in the lecture. Now moving to the next part. So yes, this is correct. Um, so first is perceptron. Sorry, first is the squad loss. So squad loss.
Last option.
Is not given.
It's not given.
Okay. Maybe this is negative. Yeah, so this is correct. And what we saw is my B is logistic loss and C is hinge loss. So B is logistic loss.
E option. E option.
So yeah, D option is correct.
Option D is correct.
Option D is correct. Yes, option D is correct. Okay. All right. So this was more about identifying the graphs. I mean, identifying the loss function for these graphs. So we know this is all right. Okay. So the next question that we have is on sigmoid function. So my sigmoid function is defined as 1 upon 1 plus e to the minus z. So which of the following is true for the sigmoid function? What do you think? Like how does a sigmoid function look like?
A and D are correct.
E and D are correct. Okay. So you're saying function is continuously differentiable and the function is bounded between 0 and 1. What about option B? And what about option C?
It is not monotonic because it is changing, right?
Yeah, so how does my graph look like?
And at negative infinity, the value is minimum, not maximum.
So we know that this function is bounded between 0 and 1. This is correct. Function attains its maximum when z tends to minus infinity, which we can see from here that this is not
Minimum.
correct because it attains its minimum, right? So this is wrong. The function is monotonic. So what is mean by monotonic function?
Strictly increasing or decreasing.
So if your x is greater than y, your fx should be greater than fx of y, or vice versa. If x is less than y, fx should be less than f of y, right?
Then this should be monotonic, right?
It should be also be monotonic, right? Yes, because we can see here as the value of z in as this value is increasing, my this function also is increasing. The sigmoid function also is increasing. The value is increasing between 0 to 1, right?
Correct.
So function is also monotonic. And option A is of course correct because that we can see in the graph there is no sharper points and edges, and this is a continuous function. So option A is also correct. So function is continuously differentiable. So option A, B, and D is correct. So any doubt in the second part? Is it clear why the function is monotonic also?
Yes, ma'am.
Okay. All right. So this next question is about the neural network. And here what you are seeing is, so this is my input layer and these are my hidden layers, okay? And this is my output layer. Now, so we have two hidden layer, one output layer. So the input to the network is a column vector x belong to R3. First hidden layer, so we can see both of these hidden layers has 3 neurons, right? So the first hidden layer has 3 neurons, second hidden layer has 3 neurons, and output layer has finally 1 neuron. Now each neuron in the lth layer is connected to all the neurons in the L plus 1th layer. So we can see this, these are connected, right? So each neuron is connected to every other neuron in the next layer. Now all the neurons in the hidden and the output layer uses sigmoid activation function. So both in this layer and this layer, the activation function that we are going to use is the sigmoid function. So my a of x or a of, let's write a of z is 1 upon 1 plus e to the power minus z. So sigmoid function we are using in both of these hidden layers as the activation function. Now, assuming that the network uses the cross entropy laws, so we'll use the natural log over there. Uh, you have to answer these two questions. So the first question that we have is how many parameters are there in this network?
Is it 21?
28.
Okay.
28.
28.
Twenty-eight.
So yeah, one point that I missed to tell is here we are also saying each neuron has a bias connected to it, except the input layer. Now, what is the answer? I guess somebody said 21,
28.
someone said
28.
28.
28. 28 is the right answer, right? So all of you, it's clear why 28 is the answer.
Ma'am, then three parameters for the input layer and then one for the bias. So four per neuron and in total seven. Correct?
Yes.
Okay, okay, got it. I was the one who said 21. I assumed three per
Ha.
neuron.
Yeah. So because of the bias, you have 7 extra um, weights or parameters that is there. So
Got it, got it.
yes, 28. So that's the correct answer. So we can see total number of weights. So for each, like here, one each is connected to every other neuron. So you will have 3 times 3, 3 times 3, 3 times 1. So 21. And total number of bias that we have is 3 over there, 3 over there, and 1 over here. So total of 7. The total number of parameters is 28. Now the second question that we have is I will just keep this figure. So the output of the second hidden layer, which is this layer, right? So the output that we are getting for this hidden layer after applying the activation function. Okay, once you have applied the activation, so whatever you got here, and you applied the activation function on that, right? So the output that we are getting is zero point 0.2, zero point 0.5, and zero point 0.8. Okay, so if this is the output we are getting after applying the activation function, then you have to find the cross entropy loss if 2, 1 minus 1 is the weight of the ith element and 1 is the bias. So, are you aware of the cross entropy loss? Like what, like how do you define it?
No, ma'am. P log P plus 1 minus P log P.
Yeah, so correct. That's correct. I'll just write it here. So, maybe you can use that. So, cross entropy loss, right? I'll just write it here. You can find it. Give me some time. So, the cross entropy loss is given by minus of P log so here you have
So it is weightage times the log of
log of
probability.
yeah.
P is the true weight, whereas the log weight is the, what do you say, P hat, yes.
Can you repeat?
The first parameter, that is P, I think is the true label, whereas log of the, that you have to
Yeah.
multiply with the log of
Yeah.
the
Correct.
P hat.
Yeah, P hat. Mm. Yes, if I could just see, sorry, stick to this one.
Is the answer 1.602?
1.602. Okay, I'll just write it.
What base do we have to take?
It, use log base, natural log.
Okay.
In the lecture, they are not specified, so I just used the normal log base 10. I'm not sure if that will give the right answer.
Correct. I mean, I said the same thing.
I think
I
they have
think
mentioned the
natural
natural
log.
log
Yeah,
then.
use natural log.
Okay. Then my answer would probably be wrong. Okay.
3.68.
3.68. Okay.
Yes.
Yes, got the same value, 3.688. Same.
Okay. Anyone else? Okay. Any other answer do we have? Or all right. Let's go through it. So what was given to us is that the output of the second hidden layer is 0.2, 0.5, 0.8, right? And we have to use the cross entropy loss, where the bias that we have to take is 1. And the weight is given to us, which is 2, 1 minus 1, right? So we know that the output that we will get, uh, I mean, after this is the output that we got, right? And once we apply this weight vector, so the final output, W output, we know that we have to, so whatever you got after applying the activation function, right, times the weights. This is what, uh, uh, I mean, you take the dot product and this is the weight, the final output that you get. So we take the dot product because you have, so this term over here is 0.2, 0.5, and 0.8. And the weights that are given is 2, 1, minus 1. 2, 1, minus 1. Right? So we solve for it and we get W out to be 0.1. But then there is the bias term also involved, and that is given to us as 1. So if 1 is the bias, we'll add it over here. So the overall, the output W out that we get becomes 1.1. All right. So if the out, so you had three neurons over here in the second layer, and from there we got um, the final output, and this W out that we got is 1.1, right? So if this is 1.1, we know, like, to get the final output, what do we do? Since it's a classification task we're dealing with, we apply the activation, since the activation function that we are using is sigmoid, we apply this sigmoid function over here. And once we apply the sigmoid function, what we get is, so sigma of 1.1, right? And this is going to be 1 divided by 1 plus 0 minus 1.1, and it becomes 0.75. So now this is what the final output that we have gotten. So as we saw that the cross entropy loss will be given by uh, what we had said is sum over minus p log p hat, right? So here in this case, what is my p here? So the prediction y is so y is 1, right? So it is given to us. The final output is 1. Okay. So if the final output is 1, I know this is the y that is the true y. So that's why we have written minus 1. And then log of y hat. So y hat that we got is 0.75, right? So minus 1 log 0.75. And then we have to take 1 minus whatever the output is, which is 1 minus 1 and log of this. So final answer that we get is 0.29 after calculating everything. So how are you getting this as the answer? I was not sure. How are you getting 3.78? Is there something that you missed in between doing it? How are you
Adding
getting
the bias.
3.67? By adding the bias, yeah. Mhm.
I think we confused it with the categorical cross entropy, wherein we add all the p log p values. So we had calculated for we took p as 2 and then log p. So the inner p we were inserting point 0.2. So 2 times log of natural log of point 0.2 plus 1 times natural log of point 0.5 without actually finding the actual output. So I think yeah, that was.
You were saying this one?
Yes, yes. So 2 times. So there's another actual loss, the two value
Okay,
minus
okay.
one. So 2
So,
times log of point natural log of point 0.2 plus 1 times natural log of point 0.5. So added up
okay,
to that.
okay.
So here the predicted value is 0.75, whereas the actual value is 1.
Correct, correct,
Yes.
correct.
The
Is
because
it?
the
Am I correct?
yes, because here if you see the true y is also given to you, right? Here it says the question says the true output is 1, right? So if the true output is 1, how does this work? So we have the input layer with us, and we are saying we have two hidden layers. So each hidden layer has three neurons, and we have one output layer. So all that is okay, and at the end we got something, and from here we'll get w out, right? So this w out was given by sigma of, so even inside, right? So even inside we had like um, whatever value you got after applying the activation function, you had to take its dot product with the weights of these, right? So that
W
we
dot
applied,
x
and
basically.
plus d. So this is the W
1.1.
out that we get, sigma of this. So once we applied the sigma of this, what we got is 0.75. So this is basically my W out. Mhm. Huh. So yeah, so sigma of this is what we got as 0.75. I think at the very end of the lecture, this has been done for the classification case,
So
if you
suppose
remember.
it was
Yeah.
not 1, it was the output of the thing was not 1, it was zero point 0.9. Then how would it change?
Output, which output are you saying?
Instead of 1, the output of the
Uh-huh.
true output is zero point 0.9. Instead of 1, it is zero point 0.9. The one which you have put in the square now. Suppose it
Okay,
is not
this,
1.
but it will be 0 or 1, right? I mean,
Okay,
we are
right.
talking
It's
about
a
the
classification
classification here.
problem.
It's a
Yes, yes.
binary output.
So what you're getting after applying the sigmoid function, you're getting the probability, right?
Right,
You're getting the probability here. I mean, 0.75 is the probability.
right. So either
Now,
this label is
hmm,
either 1 or 0. Yes.
yeah, yeah.
And from the neural network, the predicted value you are getting is 0.75.
0.75 is the probability of predicting the label as
Predicted probability.
predicted probability. Yes.
Right. So the answer is minus natural logarithm of 0.75. Minus
So the
natural
answer is
logarithm of minus logarithm of
minus
0.7.
0.75 minus 1 minus 1 natural log of 1 minus 0.75,
So
which is
second term is 0, right? Second term is
second term
0.
is 0. Yeah, yeah, correct. Mm.
So minus natural logarithm of 0.75.
Yeah, so that is 0.29. Is it okay? All right. Okay. So the next question that we have is from the ReLU function. And so you're given these values, which is minus 2.7, 3.9, and so on. And you have to find out, like, if you apply the ReLU function to these values, what will the output be?
The
E
last
option. E option.
C option.
E.
E,
last.
E.
Last.
Yes, that's correct, right? Because we know the ReLU function is defined as, so the ReLU function is defined as Z if um,
Z is positive.
Z is positive and zero otherwise. And we can see only for these three values we have Z2 positive. So that stays, and otherwise for every negative values it goes to zero. Okay, so this is the next question. The question says, which of the following losses penalize some of the data points which are correctly classified? So we had seen these four losses in the starting: SVM loss, squad loss, logistic loss, and perceptron loss. So what the question asks is, like, which of the following losses will penalize some of the data points which are correctly classified?
Squared
What do
loss,
you think?
Well,
squared loss.
even SVM and logistic also, I think.
Yeah.
SVM doesn't penalize correctly, only
Mhm.
the margin violations and they misclassified.
No, you think about the graphs that you had seen.
SVM squared loss and logistic loss. Yes.
Yeah, this is the correct answer. It's true. So,
Yes.
how did the graph of all these look like?
It was still above zero in positive side.
Yeah. So, it looks something like this, right? Squad loss you can see here in blue color. SVM one is the green one. Logistic is orange, and the perceptron is the violet color. So, we can see that for even for these like whenever my W transpose xi y, even it was greater than zero, still for some of these for squad loss, system, and logistic, we can see the loss to be loss to be positive,
Positive.
right? For some areas,
Even if
only
it
for
is correctly classified.
even if it's correctly classified. Only for perceptron is we are seeing that if it's correctly classified, the loss is exactly zero. Rest for every other cases, at some point, it is getting non-zero. That's why the answer was squad loss, ST and logistic. Okay. Okay. So this is next question. The question is when. So this is from the perceptron and basically perceptron loss. So you would also have seen this. So it says when perceptron makes a mistake, the update rule is given by my W transpose WT plus 1 is WT plus X, right? This is what we know. Now we can think of this iterative process as stochastic gradient descent by sampling one data point. So in stochastic gradient descent, we found the gradient of the objective function with respect to an input variable and use it in the update rule. So what is the objective function for the update rule, assuming the learning weight is 1?
Second option B.
Second option, okay,
Second of B. B.
this one, right?
Yes.
Okay.
This
Uh,
one B.
why do you think this should be the option? This should be the answer.
You take the gradient of this function with
Mm-hmm,
respect to W, it will be minus xy,
mm-hmm,
and you apply gradient descent to that. You will get the same function which you get the W, that is the perceptron corrected perceptron equation, that
hmm.
is the first one
Yeah,
which
yeah,
is
right. So, all right. So we know from this stochastic descent that my W t plus 1 is WT minus eta grad of F WT over W, right? And it is asked you take eta to be 1. Assume the step size is 1. So this is what we get. We use a perceptron. At the end, we'll reach this. And only using this as the objective, we can get the gradient to be minus of xy. This is the right answer. Option B. Any doubt in this question?
No, ma'am.
Okay. So we have one last question. Okay, this was not from this week. All right.
model dependent is the first one, that is W square, W square by 2, and
And
data
also,
dependent is the second one.
yeah, and also regularizer is the first and loss is second.
Yes, that is already given there.
Oh, okay, okay.
Let us match the following.
No, no, it is not given there. You're supposed to tell like
So A will
A, B,
match to
C,
1,
D.
B will match to A will match to 1, B will match to 2, C will match to 2, and D will match to 1.
B will match to what?
1.
B
D
to
will
1
match
1.
to 1.
Okay. What about C?
B will match
B
D
is
will
2.
match to,
Oh, you're
Second.
saying D. Okay, okay.
Yeah.
and
B
the
and
other two will match to 2.
The first one is okay. I mean, we know this is a regularizer term. If we talk about the loss, so the loss, yes, the loss is given by this term. So this is also okay.
Hinge loss.
Hinge loss, right?
Hinge
Hinge loss
loss,
it is.
hinge loss. Yeah, this is also okay. And data dependent, of course, we can see C1 is the data dependent, and model dependent is fourth one.
the only
Yeah,
option I did not understand, or I have forgotten what regularizer is supposed to mean. Can you just maybe?
a regularizer. So regularizer is supposed to like bring down your MSC, like the loss in some way.
Okay.
So if you go back to your ridge regression or lasso regression, right?
Yeah.
So this is, if you look at ridge regression, we saw that um, whatever we were adding in MSc, we were adding this extra term, which is lambda of norm square by 2, right? We
Right.
were adding this. And as you keep on increasing the lambda, I mean, it is putting more and more higher penalty on W, some of the weights, and it is trying to bring down some of the weights uh, uh, down, right? Not
Okay.
exactly zero, but it is trying to pull it down. So that all those redundant, whatever features are redundant, we can ignore them.
Okay.
Yeah.
Got it. Yeah.
Huh. Yeah. So yeah, these were the only questions that we have. It's, I mean, not much is covered in week 12 also. So any doubt that you may have?
Ma'am, are there questions on
Hmm.
back propagation asked in the question in the exam?
No, no, back propagation has not been taught at all, right?
In the last 12
No, no, it is just
videos,
introduced. I mean, it is not taught. I mean,
it is
that
not
all is a
going
part
to
of DL.
introduce. Correct, correct.
Yeah, that is all part of DL.
So
So
as a
don't
concept,
worry.
it,
Like,
it can be asked.
no, no, no,
Okay.
not really.
Okay, ma'am.
So you don't have to go till back propagation. Yes, Vishal.
Ma'am, I have one doubt that in logistic,
Mhm.
we can kernelize that as well. And in the hard margin, when we go to the soft margin, sir has said that you can kernelize it as well and incubate the non-linearity part. But in some of the questions, when we have option for both logistic and SVM also, I mean soft margin SVM, we choose the soft margin SVM and
We choose the um. Sorry, I lost you. Anyone
so
else? I
sorry.
lost you in between, Vishal. Can
Hello.
you, from the logistic loss where you started, can you repeat
Uh,
again?
uh, I wanted to ask you that if the question is there that which of the following can be kernelized, and if the logistic regression is there, so should I choose the logistic regression or I should leave it? Because it can
Oh,
be kernelized, but in lot of questions I have seen that they answer it as incorrect answer.
no. What was the complete? Your question was if we
My
get any question like which of the following can be
like
kernelized,
yes,
and
ma'am.
what are the options?
So option was like logistic regression and hard margin and soft margin SVM. So we go for the soft margin SVM. Like it can be which of the following can incubate the non-linearity? It was the question. So we had logistic and we had hard margin and all that. So hard margin I avoided because it is clearly mentioned that it should be totally linearly separable. Then only it can work. But in logistic we can work around with the non-linearity as well because we have we can canalize it. Hello.
Oh, yeah, yeah. I
So
got
it
your
has
question.
created a doubt, I think, in my mind.
Where did you see this question? I mean,
Ma'am, I saw, I think, in the quiz practice or some, I somewhere saw, but currently I think I cannot show
see,
you.
logistic, of course, it can be even soft margin, hard margin, all of these can be, but um,
We have
I
to
think
go with the, sir, what
all
sir has
three,
taught.
all three has to be correct in that case. But if you tell me the complete question, it will be more helpful.
I
Do you
think,
have the question with you?
no, ma'am, right now I do not have. Sorry.
Okay. Mm,
Okay, ma'am. Thank you.
okay. Anything else? Any question anyone has? The exam is next week, yeah.
On 13th.
13th, yeah. 13th.
Ma'am, for week 12, I have just today I completed the videos. I was solving
Mm-hmm.
the practice assignment. It is easy. I have tried solving, might have made a little mistake. Is it okay if we discuss the practice assignment problems?
Um, yeah, but isn't it
Otherwise,
discussed
I'll.
in yesterday's session?
Okay, I was not there yesterday. Might have.
It is discussed.
Okay,
Activity
okay, I'll
bank is
check the recorded
discussed. Yeah,
video
yeah.
then. Okay, okay.
Okay.
So next week we'll have revision sessions.
Next week we'll have the revision session. Yes, so we'll update the schedule in the calendar.
Ma'am, one last question. What is usually the weightage distribution for quiz one, quiz two, and the last part?
So end term will be more on week 9 to 12, and remaining would be week 1 to 8. So you will have full course like week 1 to 12, but most of it will be asked from week 9
So
to
higher
12.
weightage would be there for the end.
9 to 12, yeah,
Nine.
because you have not been tested on these topics, so
Correct, correct.
that
Okay,
will have more weightage.
makes sense.
Anything else? Okay, so we'll get back time and yeah, so study well. You have exam, final exam the next week, so just start revising also. Okay, all right. Thank you everyone.